Okay, in this video we're going to talk about how to deal with diprotic buffers and how to make them. And you can extend this easily to triprotic buffers. Okay, so what we're going to do is we're going to attempt to make a, what did I choose? 0.2 molar, 1 liter of 0.2 molar malonic acid buffer, and let's just pick a pH equal 5.00. I could have picked any pH. It has to be within plus or minus 1, so I could have picked a pH between 1.8 and 3.8, and from here I could have picked a pH between, I should write pH range, I could have picked a pH range between 4.696 and 6.696. Those are good buffer ranges. I picked 5, so that's in this range here. Okay. The first thing I tell people to do is to, I'm going to scoot up because I'm going to need some room, is to sketch out a titration curve. And it doesn't have to be accurate. I just want something that I can label. Now, if this is a titration of H2A, this would be H2A, this would be HA minus, and this would be A minus 2. This pH in our system is going to be pH of 2.847. and this pH is 5.696. And these are the buffer ranges, here and here. If I get outside of that buffer range, I no longer have a buffer, and it's not good. So that's the first thing I do. And so since I'm close to that one, I'm going to use the Henderson-Hasselbalch pH. I'm going to start it up here a little bit so I have some room. pH equal pKa plus the log of the base over the acid, and I get, when I solve this, 5.696 plus log of B over A, and I get B over A. This should be easy. I mean, you guys should be able to do this at this time. 0.2014, so B equal 0.2014A. And I told you it was going to be 0.2 molar. That 0.2 molar is the mass balance. That's the total concentration of A. So that's H2A plus HA minus plus A minus 2. Okay? And so that's 0.2 is equal to B plus A. I do a plug in here, and I get, when I solve it, 0.2 equal 0.2014A plus A, which gives me A equal 0.1665, and B therefore will equal 0.2 minus 0.1665, which will equal 0.03335. All right. So those are the ratios I must get. I must get the base 0.0335 and the acid 0.1665. So if I think about that, it's going to be in this range right here. If I can get my pen to work, it's going to be right in that range. Okay. Now I need to get a ratio of A to B of that, and there's numerous ways to do it. I'm going to sketch some out. Number one, I could start with H2A. I could start off with 0.2 moles of H2A. That can be gotten any way, through mass or by volume. Mass, molarity and volume, and mass and molecular weight. 2 ways to get 0.2 moles of H2A. And then I can add, what would I add here? This is an acid. I need to be increasing the pH, I need to be going pH up. So I need to add base. So I add enough sodium hydroxide to get me to this buffer region right here. This is our buffer region. Okay, which is going to be 0.2 moles to get to the first HA minus, and then a little bit more. Okay, it's like a diprotic titration. So I'm going to have to add sodium hydroxide, and I'll add 0.2 moles plus enough base to my acid, 0.0335 moles, to give me that little extra kick to get me right up into here, my buffer region, pH equal 5. All right. Now, that's one way. Another way is I could start with, let me put that in black, I could start with something like NaHA, and that could be get 0.2 moles either by mass or volume and molarity, either way. And that's starting me right here. Okay, that's this point right here, right at the equivalence, first equivalence point. So in this case, I've already somehow or other added the 0.2 moles to get me there, so I don't have to worry about it anymore. So, okay, I redrew the titration curve over here, and I forgot where I was at. So I know we're starting here. Sorry, more fiddling around. Okay, so I know I'm starting right here at HA minus, because I have sodium NaHA, the sodium malonate. All right, and so all I got to do is I've already added, I can think about it as already getting it, the 0.2 moles here. So all I got to do is add a little bit more sodium hydroxide. So I can take 0.2 moles of this and add 0.3335 moles of NaOH. The third possibility is to start right here, is to start at A minus 2 over here on the right. A minus 2. And so that would be something of the order Na2A. Okay? And again, I need 0.2 moles, because that's the analytical concentration. I can get it either by mass or molarity, or I could use volume and density if I had that. All kinds of different ways. I could do mass percent. That would be awful, but I could do it. Okay? And so in this case, too basic. I need to get more acidic, so I'm going to add HCl. And I already got my 0.2 moles. All I got to do is down here, I'm not going through to the through this equivalence point right here. I'm not going through it. I'm just going from here to here. Okay? And so in that case, I would add acid, and I would add the conjugate amount. I couldn't find it up there. I know it's there, but it would be add 0.1665 moles of acid, HCl, strong acid. That would bring us down to this position right in here, right where I need to be. So those are the three possibilities. I can start at H2A, HA minus, or A minus 2. And I'm going to ask you, and could ask you, any one of those possibilities, and you have to figure it out. This gets complicated, because there's a lot of ways to get my 0.2 moles. Okay, I've gotten it three different ways there, and you know, it is what it is. Okay, I can ask you to go from anywhere to anywhere. I can go from A-2 to 2.847, HA minus to 2.847, or I can go H2A to 5.696, HA to 5.696, A minus 2 to 5.696. So however that works out is what you have to do. Okay, now we can extend this to diprotic, and that's what I drew, a diprotic titration curve with pH on this side, volume of sodium hydroxide. And again, whatever I want. If I have 2.0 molar and I want a liter of it, you know, I can start with 0.2 moles here. I could start with 0.2 moles here. I could start with 0.2 moles here. I could start with 0.2 moles here. And I could go from H3A to right here. I clicked on the wrong one. I could start with H3A and go to this pH range. In fact, I'll put the pHs in there. There's the pHs, H3PO4 and NaH2PO4 have a pKa of 2.148, and if I'm between these two right here, that gives me a pKa of 7.198, and if I'm between the sodium phosphate and sodium hydrogen phosphate, I end up with a pKa of 12.735. So I can go anywhere, from anywhere to anywhere. 2.0 molar phosphate buffer liter, and if I can start, as I was saying before, at H3A, and I can go here, or I could start at A-3, put 2 moles in of sodium hydroxide, HCl, because I'm going backwards, I'm going more acidic, and add HCl, get to here, and then add the appropriate amount of HCl to get into the right buffer point. Okay, see if I can erase all those. Then I could, you know, pick a buffer range of 7.198. I could have a buffer range of, say, a buffer of 7. And I could start here. And I could add directly HA minus 2 and H2A minus. I could just weigh those out. Or I could have A minus 3 and I could come down here. Or I could have H3A and I could make my way with an equivalent and then up to here. Whatever you do. So this can get quite complicated. That's why I tell people to figure out what you have and start. Hang on. So I was saying figure out what you have and where you're going. So label these, figure out, say you're starting here and you're heading to this buffer region. It becomes very clear what you have to do. If you're heading to this buffer region, you're starting here, it becomes very clear what you have to do. So it's really important to know where you're starting, and these are your starting points. One thing that I haven't mentioned is I could directly add any two of these. Now, this is a long loop. Directly in for A and B and be done. Okay? We'll talk about it in class.